Well, basically, there are two parts to this talk. The first one is really in combinatorics, in the proper sense of the word, I think. And there is actually a theorem in the first part. Second part is non-commutative geometry, and I think should be called a speculation. Actually, there is a secret part 0, which is also non-commutative geometry, but it should be called inspiration somehow. And this part will be left out. I think. Well, we will see. Anyhow. Yeah, no, but this is very strange for me. I mean, it turns out that many things you can strip later of non-commutative geometry. So that you could also say that we will approach the boundary of non-commutative geometry and somehow jump off, or whatever. Anyhow, good. So let's start with this combinatorics part. Combinatorics part has input, a graph. So graph consists of vertices and edges. So let's say we have n vertices, m edges. I hope I will be consistent in using the use of these numbers. It will be a finite graph. It could be what graph theorists call a multi-graph. There could be several edges connecting two vertices. But let's say, and I don't think this is necessary, but just so I don't get complications in making wrong statements, let's say there are no sinks, so nothing that just runs out like this and stops, and let's say there are no loops. And the theory properly corrected works also with loops, and we certainly also did it for sinks and loops, but let me just not do this. Let me actually also put here connected. Quite amazed that in graph theory there are quite a few papers about disconnected graphs. Anyhow. So there are going to be two pictures of how to look at graphs, and I was somehow thinking of dividing the board into approximately, it's not a mistake that I say two pictures and make 3 columns. So there is a picture in which you formulate everything in terms of vertices. So I'll do this on the left-hand side. And this is the most well-developed theory. In algebraic graph theory, there's a lot is known about this part, you will see. But what I want to concentrate on and prove a theorem in is in the edge picture. And just for fun, actually, as I was preparing the talk on the train, I was thinking maybe we should do a kind of speculative column here, which is not about graphs, but which is about curves x over finite field fq. Curve should, not the field, but the curve should have genus G. Yeah. And there is some analogy in these things, and here will just be a kind of maybe partly speculative analogy to what I will discuss here. So what I want to introduce here is something called reconstruction problems. And to do this, I'll show you the main algebraic ingredients of this thing. In the vertex picture, there is a matrix. It's very important, adjacency matrix. Adjacency matrix A. This is a matrix which is vertex number of, oh yeah, we have a letter for this, n. It's an n by n matrix. It has entries in the integers, actually in the natural numbers. And it's going to tell you, it's indexed by the vertices. It's going to tell you for two vertices whether or not they are connected. So this will be 1 if v1, v2 is an edge, and 0 otherwise. No, not if, but otherwise. Maybe I should also say that this one is not oriented, so unoriented. Yeah. It's going to be, well, no, it's multi. It could be multi, so it could be this, and then this vertex to this vertex has 4. That's not a loop. This is a loop. Sorry. Sorry? I don't understand what? Oh, no, not the one. Oh, sorry. No, this is correct. Sorry. This number was wrong. Yes. Oh, now I understand the confusion. Yes. So it should be the number of. Oh, actually, we could just say it's the number of edges. Okay. Thank you. Yes, the number of. Oh, okay. You could say it's the multiplicity of this thing in E. Yes, thank you. This multiset. So the elements in this have multiplicity. You put this multiplicity. Yes. Maybe I should just do graphs. Well, no, it's not necessary. Okay, good. Yes. So here's this matrix. And here's another matrix. I don't know a good name for this. Yeah. Let's call this the edge adjacency matrix. And this matrix is called T. And now this T is a 2m by 2m matrix. And this 2m by 2m matrix, this is gotten as follows. It's unoriented. But now we choose an orientation. So we orient every edge in, so to speak, both possible ways. And so you get 2m oriented edges. If you so want, if you have an edge here in the original graph which is unoriented, now suddenly you choose an orientation, and there is also going to be the edge with the opposite orientation, which will be denoted like this, E bar. So E bar is opposite orientation to E. Yeah, now you have these 2m oriented edges, and this matrix T is going to be defined on such 2m oriented edges. So let me just call it E1, E2, and let's do the following. Yeah, so this is really a 1, 0 matrix. So let's put a 1 if, oh yes, so let's also introduce a notation for such an oriented edge. It has an origin, OE, and it has a terminal vertex, TE. So origin, terminal vertex. So let's do this. And now, if the terminal vertex of the first one is equal to the origin of the second one, so if it kind of flows like this, then there's a 1. But it should not be true that E2 is E1 oppositely oriented, because this would be walking backwards. And we don't want to count back. We want to count non-backtracking walks. The main point of the middle picture is that it is going to count things related to actual walks that you would make. Like, I don't think you would jump all the time back to where you have just been, but you would just want to walk forward. So this is this. Sorry? Not equal to, yes, you're right. And here should be 0 otherwise. Yes. So this operator, the edge adjacency matrix, I think first found in this generality in work of Hashimoto on the Ihara zeta function. This kind of plays an important role in the theory to come. With this, well, no, this is not good. Yes. Sorry? Yes, sure. Yes, you can walk back through another edge. Yeah, so this is considered a non-backtracking path because you take a different route, so to speak. Yes, exactly. Okay, good. So now this this A matrix, adjacency matrix, has a characteristic polynomial. The name for this was, oh yeah. So let's do call it chi of the graph, or chi of A in lambda. This is just going to be determinant of lambda minus A. And this is a thing which contains a few interesting graph theoretical invariants. And I'll tell you a little bit more about that. Here we find that characteristic polynomial of this T. And this is actually, yes, I actually need to change this to the convention which is normally used in the Ihara zeta function, the, so to speak, palindromically changed characteristic polynomial of the T matrix. This is a famous function. This is actually 1 over the Ihara zeta function of the graph. So here is a thing, Ihara zeta function. The Ihara zeta function is something like maybe the Selberg zeta function or so. You can define it as a, well, a priori formal power series like this. Do this. It's going to converge. Well, actually, it's going to be just 1 over a polynomial. And you go over prime cycles. So prime cycles are cyclic walks, which are not multiples of another cyclic walk. And you only take them, so to speak, up to enumeration of the edges that you're walking in. You would think that's like E1, E2, E1. No, it's E1, E2, E1, E3. No, E1, E2, E3, E1 is 1, but E2, E3, E1, E1 is also 1. Actually, except that this doesn't make sense. But anyhow. So, well, you understand what I mean. I mean, if you walk like this, if you start counting here or start counting here, this is the same cycle in this product. Yeah. Anyhow. Good. Yes, so you can already see here that this is important for counting lengths of walks in this thing. And here you see that this is actually a linear algebra problem, which is just finite in the graph. You just make this matrix. And after having made this matrix, you just compute this determinant. So here is actually, you could read this as a theorem about the Ihara zeta function being 1 over this characteristic polynomial. Okay. So now we get to the... yes, so I actually did want to fill this column a little bit. So here you also have an operator. The operator that you have here is the Frobenius of this ground field. And the Frobenius of this ground field acts on the vector space, and maybe in an alectic vector space, it can act on this theta module thing. So just change to the algebraic closure and act in the L torsion points. This acts on this, and the characteristic polynomial of this thing is going to be like the zeta function of the curve. And I think the conventional variable here, let's call, actually I also call it U. There is this little polar part coming from the other cohomology groups, and then this thing, the determinant of 1 minus this acting on this space, is here. So in a sense, here is a certain analogy between this 1 over this and this. And what I want to describe now is reconstruction problems. And I think it will be fun to try to see whether there is a reconstruction problem here. I think this has not been done yet. So let me now describe this next thing. The next thing is that a graph actually has something called the Vertex Deck. The Vertex Deck, D, V of the graph, this is a multiset. It contains the graph with, one after the other, all the vertices deleted. And I have to tell you what it means to delete a vertex. To delete a vertex means to delete a vertex and all edges from V. So for example, if you have this, so let's do an example. Let's do this simplistic graph. If I delete one of the vertices, I just delete also this, I'm only left with one line. And this happens for all 3 vertices. So the deck, vertex deck of this thing is just this set. Let me just indicate that you have this 3 times like that. Yeah, here is a thing which is given by a graph theoretical operation. The graph theoretical operation is deletion of vertices, which means deletion. No, certainly not. No. So for example, you could be deleting something which is on the bridge, and then this is not necessarily connected. So the elements of this are not necessarily connected. Okay. So here is this vertex deck, and for the vertex deck, there is a really famous conjecture. So let me put this up here. This is called the, it has some names associated to this, Kelly and Ulam Reconstruction Conjecture. It's from the 1950s. Actually, Ulam put it in a problem book. Kelly was one of his students that worked on the problem before he actually put it in a problem book somewhere. And it says that if the number of vertices, we have the number for this, n is larger than or equal to 3, then dvx determines x up to isomorphism. Yeah, everything is up to isomorphism. what is given V. V, this is notation. No. V runs over all vertices. Yeah. This is just notation V because there will be something there called E. Okay. We could call it, yeah, no, let's not change it. If you know all deletions up to isomorphism, and of course you don't remember what you have deleted, right? I mean, this is the main point of the conjecture, is that you know only these things up to isomorphism, so you know only these things, mid-multiplicities, then you should know the graph. An isomorphism, it is just a bijection of the vertices that respects the incidence relations given by the edges. So metric isomorphisms, if you want, if you put a unit metric on the edge. Okay. Yes, so also you can see that doing multigraphs on this side is maybe, no, let's do it on this side. Oh, let me first explain this. So now here you have a thing called edge deck. The edge deck is given, let's put an E here, not to get this confused, is a graph minus all edges. And just, I mean, an unoriented graph, and just take out the edges one after the other. So if you do the edge deck of this graph, which is not my favorite graph, somehow you get this 3 times. So this is something else, it's this 3 times. And now you can guess what should be here. Here is the edge reconstruction conjecture due to Harari in a bit later, maybe in the 60s. It says if you have at least 4 edges, then edge deck of X determines X. And some things are known, but actually very little is known. So like it is known for something like, this is known for possibly disconnected trees. This kind of weird things. It is known that this one implies this one. And I'll say a few more things later. Let's see. Yes. Once you are faced with such a conjecture, the way to approach it, or the way that it has been approached very often, is instead of reconstructing the entire graph, try to reconstruct invariants of the graph from the deck. This is called the deck. Actually, an element of this is called the card. Try to reconstruct invariants from the deck, or actually try to reconstruct an invariant from knowing the invariants of the elements in the deck. So this is typically what happens. And before I get into describing some of this, let's guess. Actually, let's try to make an educated guess of what would be the deck of a curve over a finite field. So I was a bit. Oh, actually, maybe it should be put there. Yeah. So what is this? Yes, I didn't think a lot about this, but I was actually thinking that it would be interesting to use as deck another set of curves, and a set of curves up to isomorphism, which is given by a morphism of degree larger than 1. So like a quotient of the thing. And this is maybe an interesting substitute. Actually, you can imagine many more substitutes. You could try to say, well, you could also look at covers of X and look at zeta functions of covers of X, or ask whether covers determine the original curve. And then you get much closer to this theorem that I proved with the zeta functions in finite fields, or actually curves over finite fields being determined by L series of abelian characters. So this is this way. I think this would be interesting to study the other way around. And maybe it's also really interesting if the genus is larger than or equal to 2. And I haven't thought about this, and maybe some people in the audience that get bored by the talk can think about this and tell me whether this is an interesting substitute. So certainly if you ask for the reconstruction of this invariant from the invariant, the zeta functions of this thing, at least you know that all these are going, wait, which way around is it? Yeah, these are going to divide this one. And maybe this is something like the KGV of these if you are lucky. Yeah, so. Yeah, certainly. Yeah, a smooth projective curve over a finite field, yes, certainly. Yes. Sorry? Yeah, not the morphisms. I also thought about that, but I think, and the analog here really should be just the set of curves, yes. Okay. Yeah. I think this is a, no, it should be like a bare, just like here, I mean, like a really just a set. Yeah. Well, you could also, I mean, you could think about this as, well, maybe you could say, you should look at this curve as a motive or so, and you should try to split this. And it's like in this analytic realization, it's like splitting the it's like splitting the curve maybe into characters or so. You could also say you delete motives that occur in this decomposition, and then see what happens. I'm not sure. Not even sure that this makes a lot of sense. So let's look a little bit at what is known about this reconstruction business. Oh yeah, let me actually put a result here, which is, as far as I know, the only general. Actually, maybe this section is now over. I'm not sure. Yes. Here is one result. It's a very beautiful result. There, Müller actually independently proved similar results. And one of them is that if, let me try to formulate it the right way. If this number, the average degree, is larger than or equal to twice the number log 2 of the number of vertices, then it holds. What is this? This is the average degree. Oops. Degree means degree of a vertex is how many edges stick out of a vertex. So you would sum degree of vertices and divide by number of vertices. But this, of course, adds up to twice the number of edges divided by n. There are no, sorry? Yeah, certainly. No. As simple as possible. Sorry? This is the, so we're in this column. So the edge reconstruction conjecture, so edge reconstruction conjecture, yes. You know this organization? Then this holds, yes, thank you. Maybe this was a bit confusing. Here we know much less. Oh yeah, also this is, so you see a lower bound here which depends on the number of vertices. Of course it grows kind of slow in the vertices, but I would really like to replace this by constant. And this is more or less what I'm trying to approach, but it will largely fail, so to speak. Okay, so let's put a result here, the result of Tutt from the 1970s. Tutt has proven that the characteristic polynomial of the adjacency matrix is reconstructible, meaning that if you know the vertex deck, then you know this polynomial. And the proof of this is actually not so, wait, did I put anything about this proof? The proof of this is rather interesting. The derivative of this thing is given by the sum of the chi x minus vertices, lambda. And now you just have to know the constant term. But Tutt has computed the constant term. Oh yeah, so I'll explain how you do this. But Tutt has computed the constant term, and the constant term is something combinatorial in which all the ingredients that are in this formula he can reconstruct. Yeah, it's very beautiful. So this will be a trick that we are also going to try to apply. And how can you see this? Well, you can see it as follows. You can replace in this determinant of lambda minus a, you can replace lambda on the diagonal by all different variables. And then do partial derivatives with respect to all these different variables. And you look at this determinant as being expanded according to minors, according to these elements. And then this is really easy to find. And now you can imagine the trouble there is on this side, because on this side you delete an edge, and to delete an edge means to delete two rows and columns that somehow belong together, namely the edge and the inverse edge in this side. So you will see what happens in this happens with this. So let me put up the theorem. The theorem says if the average degree is larger than or equal to 4, then zeta x is edge reconstructible. this is the main theorem for today. And I will explain a little bit how to do this. It's a bit more complicated than this. Once you know this, so you can use this polynomial to understand vertex walks, by which I mean walking from vertex to vertex, but jumping back how often you want. You can use this theorem to understand non-backtracking walks, genuine walks on the graph. And this is a maybe corollary of this thing. If the x bar larger than or equal to 4, then the number of non-backtracking walks of given length, this is an edge reconstructible. And maybe you see already this cloud of the non-commutative boundary hanging here, because you are walking off to the boundary of the universal covering tree using these walks. And this is somehow related to the measure structure on this boundary. Yeah? So I'll explain this a little bit later. Yeah, so this thing, what did I want to say about this? There is a similar result, of course, from this, but much more is known on this side. On this side, this is just a remark. But this may be important later. So Goldsill and Mackay have proven that the number of vertex walks is reconstructible, but also that the number of vertex walks, so reusable walks, let's say, also backtracking, from a given vertex, and maybe you should do closed. Oh yeah, maybe you should do closed. Well, it doesn't really matter, but the number of closed, maybe. I mean, really like walking around and getting back to the same original point. So here, closed walks from a given vertex. This is also determined by the Vertex Deck. And this is I think this is a very interesting and weird result. How do you do this? Well, you have to know what vertex you're talking about. But you do this by pointing in the Vertex Deck to the graph from which it was deleted. And this has a label which says it's this vertex. Yeah. Well, this is traces of powers. This is slightly more complicated because you have fixed this vertex. So the total number of walks is the trace of the power, and this follows from the log determinant. This one, if you are fixing a v, this is actually related to reconstructing the Perron-Frobenius eigenvector and then taking the right sum. Yeah, yeah. Exactly. This is what we cannot do. Well, this is what we cannot do here. Yes, it's a bit pity because we would like to know this Perron-Frobenius vector because this is also measure theoretic on the boundary. Yeah, so very important. Okay, so to finish this combinatorial part, let me actually show you how to prove this. This is an elementary linear algebra proof, but you somehow need to do your linear algebra 19th century? Yes, correctly. Remember your linear algebra. And there is one somehow philosophical remark which I thought was kind of cute to make in between. This is the question whether there is some, now I'm erasing the important thing I wanted to say something about. The question about duality or functional equation in the Ihara zeta function or in the graph theory setting. This is kind of important for this middle theorem. So let's see. Yes, so the first thing is, let me now actually look at this as a combinatorial formula and as a number, well, I really can't remember this thing. So, proof, well, let me just outline the proof. So, write the following thing. We write a polynomial associated to x, and we write it in multi-variables, namely as many as there are edges. And now we write the determinant of, and we have changed this diagonal matrix into one which has different variables, but it actually has the same variable for an edge and its inverse. Yeah? And now I do minus t, and this t is okay. This is like, please skip the proof. I don't know. Yes. Okay. sorry, yes. Well, I mean, enumerate or label in the same way. So E1, E1 inverse, E2, E2 inverse, so that the variable lambda 1 and lambda 2 are at the location of exactly an edge and its inverse, right? Like this. So now this thing. So now look at this, this formula. And my claim is that if D, this is a D coefficient, is larger than M, then take this polynomial, specialize everything to the same variable. So this is a comma, sorry. Everything to the same variable. Look at the coefficient of lambda to the D in this polynomial. This is a combinatorial notation to mean the coefficient in this polynomial of lambda to the D. And now the formula will actually say that this is equal to the following. It's like inclusion, exclusion. The entier of D over 2, we run with a sign. And then we run with all partitions like this. Lambda D minus 2 are coefficients in this polynomial. And now we delete these edges iteratively. And then substitute on the diagonal the same lambdas. Yeah. So this is the main formula. And this main formula, let's read it a bit. What does it mean? This thing is actually going to specialize to what we want. Well, I mean, this kind of U has become lambda inverse. This is the denominator of the Ihara zeta function. We know its coefficients, but only the top coefficients, from 2m to m, to m plus 1. We have these things, and they're expressed like this. They're expressed like this. They are expressed as coefficients of these polynomials. And these, of course, are determined by the deck, because you know the deck. And there is always something being erased. R is at least 1. So, but you have to kind of successively erase further edges. But of course, you can do this in the deck because you know the deck. So this side is reconstructible. And the trick is the usual, the trick in the proof is the usual trick with the derivatives there. Derivatives giving vertex deletion. The trick here is that second partial derivatives here in the lambda I something variables give these things. And then you just have to prove an identity in polynomials that says if you have a polynomial of degree 2m in m variables and the degree in each of the individual variables is at most 2, then you actually have such a formula involving partial derivatives. Yeah, so I really don't want to struggle through this proof. But this shows that you know the top half coefficients. So the top half coefficients. So we were actually stuck at this point with a kind of a really stupid half theorem telling that you know half the coefficients. And then I struggled a bit in trying to prove that there is some kind of duality that implies if you know half the coefficients, you know all the coefficients. And think, for example, of a regular graph. Regular graph in all this theory is uninteresting. If you do a regular graph, edge thing is the same as the vertex thing, basically. There's nothing new. But think of a regular graph. A regular graph will satisfy functional equations, just like in this hidden column, which was here, when you have the functional equation for the zeta function. And this functional equation implies this kind of palindromicity in the coefficients. So knowing half the coefficients will determine all the coefficients. So this would be really good. So what is this replaced by in irregular graphs? So I thought maybe it is something that you could call a constructive duality, just in the sense that this top half coefficient should determine the bottom half coefficients in some kind of numerical way, and maybe not in a homological way, but in such a way. And it actually took a long time before Janne said, oh, but this just follows from this formula of Bus. So let's just do this. There is a beautiful formula of Bus and Hashimoto. I mean, you kind of feel that this is true because this 2m is artificial. The real number of variables is m. But you just have all these orientations that you had to choose, and there is something fishy. But there is this formula, so to speak, replacing the duality, or replacing the functional equation. And this is how I read it now. I'll write it in the usual characteristic polynomial way. So let me explain a bit. this is the thing we're interested in, the Ihara zeta function denominator up to this lambda is u minus 1. This is an innocent thing which just has the order characteristic of the graph basically here. But it's rather big. It's degree 2m minus 2n. And then there is this thing. This is an n by n matrix. But it has a lambda squared in it. So this gives a 2n degree polynomial. And this is the usual adjacency matrix that we had. And this is just a diagonal matrix. It has the degree diagonal matrix. It has the degree of each of the vertices on the diagonal. And now if you look a bit, yes. So he did this Ihara zeta function for representations of p-adic groups in lattices, and it's in this paper. Yes. Yes. Actually, proof of this is very beautiful, linear algebra. So if you look now, in this thing, we know the top, we know the 2m to m coefficients. And now look here, you have this funny thing. You know these coefficients. So how many coefficients do you know of this thing? Yeah. So of this thing, you now know, let's see, the coefficients of this. You know the coefficients of lambda j with with j running from 2n minus m down to 2n. But these are all coefficients if this number is negative. If this number is negative. Yes. So there is nothing more to know here as soon as you have a certain relation between n and m. And this translates into exactly this relation. Yeah. This is all I can say. Well, you can just expand. This is a 2n degree polynomial. This is a polynomial that you know. And this is a polynomial of which you can reconstruct half the coefficients. You can just see how many of this you have reconstructed. And in this case, you found them all. A and d to the vertices, yeah. So this is exactly the point. So here you have this edge thing, and this is an expression which does it in terms of vertices alone. Yeah, it's kind of logical that it exists, but it's kind of interesting that it's like this. And it's not so easy to actually manipulate this thing with squares in it. This is not really linear, and whenever you try to do results about eigenvalues of this kind of thing, it's a bit complicated. You have this kind of determinant of sum results of Amitzer and other people, and if you try to apply this here, it's not so easy. But just the mere fact that this formula exists, I think, is some kind of substitute for duality in graph theory. Substitute for, and like you said before, if you're interested in this corollary, well, this corollary is just really the usual identity. I hope I remember correctly. You have traces of powers of these things, right? I mean, this is the thing that says once you know this, then you know traces of powers of this thing, and this will have in the II location exactly the number of such walks, not backtracking over edges. Yes. Okay, good. Yes. So let me now somehow switch gears and style maybe not. Sorry? The proof? No. It's writing a block matrix. Really, but this is a formula that you have to discover. This is the point. I mean, the proof is not so difficult. No. Yes. Okay. And now, of course, you can see. Oh yeah, if you look at this formula and imagine you have a regular graph. If you have a regular graph, this strange matrix D, which is there, is just a constant. It's a multiple of the identity matrix. And now you see, I mean, there's nothing new on the. It's really the left-hand side is just kind of a shift of the characteristic polynomial of the adjacency matrix. Then there's nothing strange there. Okay. Now, yes. So now, second part. I actually became interested in the reconstruction of the Ihara zeta function, or rather in the reconstruction of the Carroll-Frobenius eigenvalue of t, because this has something to do with the metric structure of the boundary of the tree, the universal covering tree of the graph. So before I start on this, let me tell you that I once very enthusiastically told the graph theorist about this, and his immediate reaction was, why should you talk about all these infinite and even uncountable sets when you're dealing with just a finite set? So I always keep this in the back of my mind, and I really hope for success. Here's my graph, just finite data. But this graph is also encoded completely by knowing the action on the universal covering tree of the fundamental group. And this fundamental group is just free of rank G and acts in some way on this tree. So we have not lost any data, but this data is maybe indeed complicated in the sense that this action is very much determining the thing. It gives the identifications, and the regularity, irregularity in this thing also relates to the graph itself. So instead of this, we pass to something easier. We pass to the boundary of this tree. So this is the boundary. Boundary means ends, right? So in this tree, we now look at the space of ends. And this thing, and this still carries an action of gamma. And now I guess the main point of this section is that this really doesn't remember anything except G. Yeah? But you can somehow soup this up a little bit, measure theoretically, so that it does remember X. Genus of the graph, yes, but genus of the graph, first Betti number of the graph. Okay? Graph theorists call the genus the minimal genus of a Riemann surface in which you can embed a graph without self-intersection. So yes, but I'm also going to say genus here. I think for this audience it's okay, right? Yes, yeah. First, yeah, cyclomatic number. Okay, so now you have this thing, and this is only going to depend on that. And the reason is really that, well, this dynamical system, so to speak, this is really the same as the boundary of the Cayley graph of the free group. So let's give this free group of rank G a name. It's called, let's call it FG. Okay, it's just this with the usual action. So if you take infinite one-sided words in the fundamental group and then act on it just by multiplying with elements of the group, yeah, then you will get that this is just equivariantly homeomorphic, so to speak. There's a homeomorphism between these things that intertwines these actions. Choose generators, choose them as generators here, make the Cayley graph and do this. And intuitively you can see it like this. This tree can be rather complicated, but there is always a kind of quasi-isometry from here to here. You know, you can, in the original tree, you can be doing this. So here's a bunch of edges. But at some point, you might hit a point which is equivalent to the original one, which is, this is a loop from x0 to x0. And somehow there is an understanding of how much this grows. So it's really, yeah, I mean, there is in the limit an identification. So there is no identification between T and, obviously, and the Cayley graph of FG. But in the limit, this is just going to be this. Not backtracking words, yeah. So exactly like we had before. So really walking without looking back, so to speak. Yeah. Okay. So now, so this middle part, yeah, so this middle part, I wanted to say one more thing about this. Maybe actually the board should be further divided. So you could look at this as a non-commutative space, as a non-commutative topological space. We build this C-star algebra, the functions on this boundary, reduced cross product with which one is acting, this one is acting, with the group. Maybe for kind of reasons that you see in dynamical systems and also in this number field business, it's interesting to do a version of this which has only functions and elements from the group, not star elements. I don't know, so let's put a dagger here and just call this the dagger algebra. This thing also really doesn't remember a lot. For example, you know the K theory of this. It only depends on G. This, you know the strict isomorphism type of this. I think this is just going to be the Kunz-Krieger algebra for this graph. Take G, a flower with G leaves, then this is going to be the Kunz-Krieger algebra of this. So it remembers only G. It's a bit like in Riemann surfaces. You know, in Riemann surfaces, if you take Fuchsian uniformization, the boundary is going to be S1. And S1 has the action of this Fuchsian group. And we also know the K theory of this cross-product algebra. I think you did this. It also depends on the genus. It has 2G minus 2 and some torsion parts, which also depends on G. But it really only depends on G. So we have this space. And we seem to have lost a lot of things. But now you can somehow recover things by going to this side of the board. This side of the board would take this boundary and this gamma, but this is really just like this Cantor set. Let's do genus at least 2. This Cantor set and this free group. But we can add to this density of measures. So we can put here for points running through the tree, a set of measures, Patterson-Sullivan measures. Measures. Well, this is what in classical Fuchsian uniformization, this is what you would do, but then what you would get here is just Lebesgue measure, I think, on this circle at infinity. So in the Poincaré disk, you go to the boundary, and then you can just put Lebesgue measure, I think. But so here you have this kind of more fractal measure. If you would do a classical Riemann surface and you do Schottky uniformization, then you would also get this kind of fractional stuff. So I actually wrote it down. It's this thing. S tends to some number delta. This number delta is very important for us. It's a sum over an orbit, e to the minus s, the distance between x0 and, x0. Let me just put in 0 here. x0 and the image, and then the Dirac measure along the orbit, and then divide by this Poincaré series. And there is this. So you can define this on T union the boundary, but after taking the limit, it will be supported entirely in the boundary, entirely in the limit set. And from above. This thing is the exponent where this starts to diverge. And this number occurs in all kinds of situations. This is actually an interesting, so this is the divergence. Yeah. You will see. I mean, it will be here. Yeah. I mean, this is, of course, going to be just a reformulation, but I think it's very cute. I mean, this is the unique KMS state occurs in delta. Oh, I'm saying the thing already. The unique KMS state occurs in temperature delta, and is given by integration against these measures, if you vary the point. Yeah. Divergent exponent of this thing. It is also, delta is also the Hausdorff dimension. Hausdorff, wait, this is embarrassing. 2s and 1f? Okay. Yeah, it must be somewhere. I was like, oh, there, yes, you're right, actually. Sorry. It's the Hausdorff dimension of the boundary in something called the visual metric. Visual metric is something that is built up. So you're on the boundary. Here is a point, another point. Visual metric depends on the choice of a base point. And you do this. And visual metric is this, e to the minus this length. So a certain length. Visual metric is e to the minus l, so to speak. And it's the Hausdorff dimension in this. And these measures are all absolutely continuous with respect to each other. And they're absolutely, you change x, nothing changes. But also this is, in a tree, this is absolutely continuous with respect to the Hausdorff measure of Hausdorff dimension delta in this metric. Yes. So it's very, and now the, so to speak, the this algebra picture now moves to this side and becomes a quantum statistical mechanical system in which this is rephrased in terms of time evolution in something called the Bouzemans function. And then you can somehow recover the metric because of this unicity of KMS states. It's very strange. I mean, there is, well, it's kind of a nice application. So let me write this down. No. It depends on the metric. I mean, it's first you have to take this Cantor set and give it a metric which comes from the internal thing. Yeah? Otherwise, all graphs would be isomorphic. Actually, in the course of this work, we have actually proven the fact that all graphs of given genus are isomorphic several times. Yeah. Yes. So let me not do this. So let me actually write this down. So if you are here in this algebra and you switch to this side and you want to interpret it on this side, you get this. As such a system, you now look at this algebra, or rather maybe actually at this non-involutive algebra, and you put a time evolution on this. Sigma goes from R to automorphisms of this thing, and T goes to the following thing. Let me just write it on a general element. So there's functions and group-like elements, and we just switch this to, and now this becomes, let's see, so this is a function of some argument, and it becomes e to the minus I t delta Boseman function, chosen point, and this is a function of the boundary variable, gamma. And this function is really just the, so let me just write down what this function is in general. So you take two internal points in the tree, and you take this thing in the boundary. And it's going to be the limit of the distance between the one and an auxiliary variable, the other and an auxiliary variable, and this auxiliary variable should tend to this boundary element. Yeah, so let me make a picture. Here is psi, and now here's an x1, an x2, and now you somehow look at a point x3, which is approaching this boundary, and you try to do this distance minus this distance. Yeah, and now let me immediately change this picture. Yeah, I mean, well, you can write this down in usual uniformization. Let's say it like this. If, let's do it in the example of x0 and gamma inverse x0. And let's imagine that psi is here somewhere so that it projects down there. Or let's imagine it's here somewhere so it projects down here. What is this Boseman function? This Boseman function is, well, let's see. We have to do this minus this. It's this part. And what is this? This is the length of the loop gamma from x to itself. So here you see the connection with this length that I am desperately trying to reconstruct. Because, oh yeah, so let me put up the main results. The main result here is that this is something I wrote down with Matilde Marcoli some time ago, and maybe now, is that this structure with this sigma, this determines x. And this is just reincarnation in non-commutative geometry of measure theoretic rigidity for using this Patterson-Sullivan measure. But if you think about it like this, you know, the main point is that you look at this thing. The first point of the proof is that there is a unique beta with a KMS beta, namely beta is delta. And then the point is that this unique KMS beta, so I mean, there is this work of Kumian and Pasque and Reynaud that actually gives you the entire theory of this. If you compute the correct co-cycle, here you know that this applies, and you know that then KMS delta is integration with respect to these Patterson-Sullivan measures, and these are all going to be absolutely continuous with respect to each other, and now you use this rigidity. It's like Mostar rigidity, but in very low rank, rigidity theorem of Cornat. For this system, you know, if you know the system which is on top there as a dynamical system with this measure, and then the graph is determined by this dynamical system of the boundary with the action of the free group. So this is just a Cantor set with the action of a free group, but with this complicated measure on it, and the measure up to absolute continuity. So the absolute continuity class of this measure determines the graph. So I think what we learn looking at this in dynamics or in non-commutative geometry is that in edge reconstruction problem, the main thing to concentrate on is lengths of loops. You have to try to find the lengths of loops. Now the Ihara zeta function becomes very natural object to consider. So let me tell you at the very end of the talk what we have done, because I haven't connected to the previous part yet. The connection to the previous part is that this delta, this delta is the Perron-Frobenius eigenvalue of T. And now this is the connection to the previous thing. So I have proven now for you that you can reconstruct from the edge deck the Hausdorff dimension of the boundary, because this is the solution to the, it's an eigenvalue of the Ihara zeta function. If the average degree is at least 4, I've reconstructed the Hausdorff dimension of the boundary. And now you have a lot of choice. You can try to reconstruct the visual metric. You can try to reconstruct the measure. You know what delta to tend to. In the measure is also only the distance between x0 and gamma x0. It's the length of a loop. You can try to look in this picture. If you look in this picture and look in the Bousselmann function, the Bousselmann function is also like the length of the loop. Yeah? So you see that what is somehow wanted is the reconstruction of these length things. So let me just put this here as the future, so to speak. Well, the future maybe. Yeah. What I said about part 0 in non-commutative inspiration is really that I would have never thought of trying to reconstruct this if you would not see in this picture that it is so important. Yeah? So in this picture here, it comes out, this is such a natural number. No, actually, it's not a natural. Oh, okay, stop. You understand. Yes. That's it. Thank you. Yes. Okay. Good. Yes. So for example, so very good would be to reconstruct whatever reconstruct here means. Reconstruct these lengths of gamma, but this should be done by pointing to gamma. So for gamma, you can choose an enumeration given by basic generators of a fundamental group, and you should know the lengths of this set of loops. Then you know the lengths of words in these, and then you can go with these words to the boundary and find this Bousselmann function. So this would be really good. Also very nice would be to reconstruct the number of closed non-backtracking walks from a given edge. And by this I mean, this is the analog of this Gottzel-Mackay result. Fix a vertex by pointing to an element in the vertex deck. Find the loops that go from this vertex to this vertex. Try to do it for edges, in the sense that point to the edge deck, look which edges is deleted, choose an orientation on this, and look only at walks that start in this direction. And if you do this, you are also very close to this. And the problem here is that, you know, this Gottzel-Mackay reconstruction, this is about finding a minor, a principal minor in a matrix in which you, by just deleting one edge and one row. And here you have to delete 2 edges and 2 rows, and this leads to very interesting old linear algebra due to the originators of linear algebra, like Jacobi, and to my amazement also there is a theorem of Lewis Carroll about this. This is the first time in my mathematical career I bumped into Lewis Carroll in mathematical sense. But it is something like this. The Ihara zeta, now I should put the right one on top. It's something like this. You know, we know this. This one certainly we know, and this we have reconstructed. And this is going to be now not just a minor. It's going to be a determinant of something. And the determinant is, here you will have this number, NRE, of length E. Length R, sorry. NRE will be here, U to the R. It will also be here. This is very nice. So we try to find this number. But here is this mixed term. It's walks that go from E to E bar in length R. Yeah, E to the R. And here is walks from E bar to E, and this is different. You are in a usual graph. So I want to know these numbers. I know this. This mixed term is a bit confusing. It's walks that pass through E the wrong way around after a certain number of steps. It's very annoying. Yes, I would also really like to reconstruct this Perron-Frobenius eigenvector instead of just the eigenvalue, the eigenvector. This is not so strange because this number is given once you know these numbers. Yeah, there is a trick. If you know these numbers, then you can know this Perron-Frobenius eigenvector. And this Perron-Frobenius eigenvector occurs here because of the following kind of thing. You can imagine that the boundary consists of cylinder sets of a given edge, so everything that sticks out of a given edge and given direction. And the measure of this is determined by how far you are from the base point and the Perron-Frobenius vector entry for this edge. So this would also be really nice to do. And let me finish by kind of even more speculative things. Once you look at the reconstruction problem in this way as being something in dynamical, sorry? Yeah, sure. Yes, but not going from a given edge to a given edge. No? I mean, this is a more specific number. In the Ihara zeta function, I can count how many walks there are of a given length. But now I want to say they go from this one and back into this edge as the last one. And only those, and not others. Is it the same, or? Well, maybe we'll see after the, well, let's see. Okay. So the final remark was, now that you do reconstruction problems like this, you might formulate a reconstruction problem, for example, for Riemann surfaces. A Riemann surface is such a thing. And inside, or you can do it in Schottky uniformization, or in this, and you have this kind of almost, what is it called, multifractal problem. You have this boundary, you delete certain edges, you get kind of sub-parts of the boundary that you know. All these sub-parts have Hausdorff measure 0 in the given Hausdorff measure, but in their visual metric, they have a positive Hausdorff measure. And somehow you get these kind of reconstruction problems, I haven't thought a lot about this, that you could also just do in Riemann surfaces now. Yeah? So this is maybe another justification for the perspective of non-commutative boundary on such a simple thing as a graph. And I really hope that I'm going to meet this graph theorist in a few years and tell him, ha, see? Anyway, okay, thank you.
Among the possibilities of nature, one is the following. After all, if you take a graph and you delete the ledge or the vertex, then there will be a corresponding boundary on this deleted set.
Yes.
And then it would be quite reasonable to say that one should be able to reconstruct the boundary of the original graph from the boundaries of the deleted set by some process.
Yeah. This is what I have tried, actually. And actually, oh yeah, maybe a good remark in this sense is I have tried to do this by the following thing. You have these very particular time evolutions, but you can play with these time evolutions and somehow vary them, and you can try to make, try to deform them so they disappear on the deleted thing. Yeah? And then it becomes, I thought it becomes a problem which we have solved. It's a problem in multi-complex variables in which you know the boundary conditions and you can make the complex closure. And it somehow didn't work, but I mean, maybe this is just my stupidity. But this is, I mean, yeah, so the idea is also that you create this flexibility on the boundary for this reconstruction problem of being able to deform this. I think this is good. Yeah. Okay.
And what I was hoping for is that you could reconstruct the boundary of the original system.
Yeah, okay.
Using these statistics and the knowledge of the boundary of the
okay. Yes, okay, okay. Yeah, I understand. Yeah, okay.
Just make a guess for what it is by looking at examples.
No, I think it's, yeah. I mean, you don't know how the boundaries sit in the other boundary. Also, you only have to prove that there is a unique solution. You don't even have to find the solution. Yeah. Good, yeah.
When I see Perron-Frobenius, it suggests something to me. I mean, if you look at the tree, unfortunately, is the so-called TNT.
Yeah, oh yeah, sorry, yes, okay.
Then you may have a backup process of the tree, and what you have is a matching boundary.
Certainly. Yes, certainly.
Doesn't make sense.
It is the same, I think, here. Yeah, it's really the same. Yeah. Yeah, it's exactly this. I mean, this is like a shift space. And in the shift space, you choose this metric, so to speak. Yeah, or this, yeah, exactly, yeah. Okay. Yes. I have tried this. I have actually tried this, but it was yes. No, I don't think so. And I have actually, I was aware of this, and I have tried to at least rewrite a little bit of this language, but again, not. Yeah, yeah. Uh-huh. Yeah, okay. As a map in graphs, graph becomes a variable in this picture. Huh? If you, yeah, exactly. Yeah, sure. Yeah, okay. Okay.